Now let's talk about the kinetics of nuclear decay reactions. So this section will allow us to connect the concepts that you just saw in the previous section with the concepts of kinetics that you learned about at the beginning of Chem 1C. Nuclear decay reactions will always proceed by first-order kinetics, and so that makes our lives a little bit easier because we don't have to worry about what the reaction order is. It'll always be a first-order reaction, and so we would always use first-order rate laws. We could study this reaction for the decay of uranium-238. It emits an alpha particle to form thorium-234. And if we wanted to calculate the amount of uranium-238 at any point during the reaction, we can use the first-order integrated rate law, which says that the new concentration of uranium-238 is equal to the initial concentration of uranium-238 times e to the negative kT. Now, one thing that is worth mentioning here, and another thing that's really nice about first-order kinetics is because of the way that the units cancel out in this equation, you can use whatever units you want for concentration here. It does not have to be in units of molarity. You could use units of grams, you could use units of atoms, you could even use other units that we'll be talking about later in this chapter, like radioactivity units. And as we go through examples, you'll see how the units cancel out and how it becomes acceptable to use whatever units you want. But that is one of the really nice things here about first-order kinetics is in the integrated rate law, because the units cancel out nicely, you could use whatever units you want. Now remember, when we talked about first-order reactions, we said that for a first-order reaction, there is an exponential decrease in the concentration of your reactant. And because of that, the concentration of the reactant will never go all the way to zero. This reaction would take an infinite amount of time to go all the way to completion. And so instead, a different marker that we can use to tell how long the reaction takes to occur is by looking at the half-life. That is to say, how long does it take for half of the initial amount of uranium-238 to react? We saw this equation to calculate the half-life for a first-order reaction. It says the half-life is equal to the natural log of 2 divided by the rate constant K. And importantly, in this first-order half-life equation, we see that the concentration of uranium-238 appears nowhere in this equation. Ln of 2 is a constant, and K is a constant, and so that means the half-life is going to be a constant for any first-order reaction. So for any nuclear decay reaction, the half-life will be completely independent on how much of the starting material you have. Now we'll take a look at an example problem. Here we're told that polonium-208 undergoes alpha decay, and this decay reaction has a half-life of 2.9 years. You're told that you have a sample of polonium-208 that initially weighs 20 grams, and it's going to decay for 4.5 years. And first, we're asked to determine what the mass of polonium-208 will be after that 4.5-year period of time. And so when the question is asking you to find what the new amount of your reactant is, after a certain amount of time has elapsed, the integrated rate law allows you to determine that. So we can start by writing our first-order integrated rate law, which says that the new amount of polonium-208 will be equal to the initial amount of polonium-208 times e to the minus kT. Now let's think about what we know in this problem so far and what we need to find. We know what the initial amount of polonium-208 is. We know that that is 20 grams. And if I plug in 20 grams here, if I use grams as my units for the amount of polonium-208, I'm going to get my final answer to be in grams of polonium-208, right? Because this whole exponential is going to be completely unitless, right? Exponentials must always be unitless. So this term has no units, so you can use whatever units you want out in front here, and you'll get the same units for your new concentration of PO208. Additionally, we're told that the sample is decaying for 4.5 years, and so we know that the value of T is 4.5 years. There is, however, one piece of information that we do not know, and that is the value of K. So now we need to find the value of K. And we think about what other information we have in the problem that will help us to find it, and a piece of information that relates to K is the half-life. We're going to use T1/2 to find it. All right, so we have our half-life equation that says T1/2 is equal to the ln of 2 over K, and then you can cross-multiply through this equation to solve for K, and get that K is equal to the ln of 2 over T1/2. Then we're going to get the ln of 2 over the half-life is 2.90 years. And so when you plug this into your calculator, you find that the value of K, that is the rate constant for this reaction, is 0.239, and the units are years to the minus 1. Now we know that, and now we know everything that we need in order to get the answer to this problem. So now everything gets plugged into the rate law, and what we have is that the new amount of polonium-208 will be equal to the initial amount of polonium-208, which was 20 grams, times e to the minus k is 0.239 years to the minus 1, and then multiply that by the time, which is 4.5 years. So what we have in the exponential is, again, it totally comes out unitless, right? Because you have years to the minus 1 and years, so that cancels out. And all we're left with is the units of grams here. And you'll find that the new mass of polonium-208 comes out to 6.8 grams. And that answers the first part of this question. Now in this second part of the problem, we're asked to determine how many alpha particles are going to be released. We're given the mass of a polonium-208 atom in units of atomic mass units. And I'll remind you, it's been a long time since we've talked about atomic mass units. We first introduced those back in Chem 1A, and I don't think we've talked about them since then. Atomic mass units are the interchangeably used with units of grams per mole. Alright, so with that in mind, we have to first think about how we're going to relate the amount of polonium-208 that's reacted to the amount of alpha particles that are released. And the key to doing that is by writing the nuclear decay reaction, because that will allow us to see how those two things are related to one another. Now, we've practiced with writing alpha decay reactions previously in this chapter, and the way that we're going to go about writing the alpha decay reaction for polonium-208 is by putting our polonium-208 on the left-hand side of the equation, and polonium is atomic number 84, so we'll just put that in there. Now, when it undergoes alpha decay, you're going to emit an alpha particle, or that's a 4,2 helium. And then we can also predict what the decay product of polonium-208 will be here by recognizing that when you emit an alpha particle, the mass number decreases by 4, and so that's going to take us down to 204, and the atomic number decreases by 2, and so that takes us down to 82. This is going to make lead. Alright, what we see from this reaction is that we have a 1-to-1 mole ratio here. It says that for every 1 mole of polonium-208 that reacts, you generate 1 mole of alpha particles. So now what we have to do is find how many moles of polonium-208 have reacted. Now, how are we going to find the number of moles of polonium-208 that reacted? Well, keep in mind that we were told what the initial mass of polonium-208 was. So we initially had 20 grams of polonium-208. And then in the first part of the problem, we figured out how much polonium-208 remained. So after the 4.5 years, the amount that remained was 6.8 grams. Therefore, the mass of polonium-208 that reacted would be the difference between these two numbers. So the amount reacted would be the 20 grams that we started with minus the 6.8 grams that remains. This means that 13.2 grams of polonium-208 has reacted. Now I can go ahead and convert this into moles and then convert it into a number of alpha particles by doing some unit conversions here. So we have 13.2 grams of polonium-208. And then we're going to convert that into moles by using the molar mass, which we were told is 207.98 grams per mole. This now converts us into moles of polonium-208. And then next what we could do is convert that into a number of moles of alpha particles, because from our balanced equation, we determined that 1 mole of alpha particles is generated for every mole of polonium-208 that reacts. So we'll add that mole ratio in here. So 1 mole of alpha particles for every mole of polonium-208. Alright, so now that converts us into moles of alpha particles. And you know what, while we're at it, we might as well just convert this into a number of alpha particles and get to our answer here. So once you know the moles of alpha particles, you can convert to a number of alpha particles by using Avogadro's number, right? That takes you from a number of moles to a number of individual items. Avogadro's number says that 1 mole of something is 6.02 times 10 to the 23 items. Alright, and now we know the number of alpha particles that have been emitted. When you plug all of this into your calculator, you'll find that it is going to be 3.82 times 10 to the 22 alpha particles that have been emitted over this 4.5 year period of time. And there we have it. So this the first part of the problem that we looked at involved using an integrated rate law. The second part of the problem here involved doing some stoichiometry in order to convert the amount of polonium-208 that reacted into a number of alpha particles that had been emitted. Alright, that brings us to the end of this video in this section. In our next video, we're going to talk about radioactivity.